Hi there, I'm Jeff Yee, and welcome to video number 6 now in the Particles of the Universe video series. And this one will be on atomic orbitals. But I want to start first with a question. And this was a question in the introduction video that began with two particles. In this case, imagine the skittle is, yellow one is a positron, and the one over here, the green one, is an electron. A positron and an electron are attracted to each other, annihilate them, and they disappear completely. But now imagine two particles with the exact same charge, the electron again, and this time a proton with a positive charge. They were identical, but yet this time the electron takes a curious path around the proton, never annihilating and creating an atom. The question is why? Why does it do that where it takes an orbit around a proton and it doesn't annihilate, yet the proton and the positron have the exact same charge? Why does it do that? Two quick reminders before starting the video. The first is that all the information in this presentation is available in both the books and on the website in the URLs you see. And the second is I will cover blue slides in detail and red slides you can pause at any time to read, such as this one, which covers the wave constants and variables that will be used in the presentation. Okay, now we're on to orbitals and the path the electron takes around the proton. If energy flows as waves, and if a spinning proton contains both an attractive spherical wave and a repulsive axial wave, then atomic orbitals can be calculated using classical physics. That's the key point there, classical physics equations, where the sum of the forces on an electron is zero. And this concept would not have been possible until very recently when the proton's pentaquark structure was discovered. And it was also discussed in the section on forces, if you want to watch that video. But here's the very simple explanation, and now it makes a lot more sense about why an electron would take an orbit around a proton, but yet it annihilates with a positron with the same charge. Because here, let's assume two forces. The first force is that the electron is attracted to the proton. If it was only this force, it would annihilate. Right? There's destructive wave interference which pushes the electron towards the proton. Yet there's also a repelling force in here. And interestingly, the fine structure constant, the same one that is used for the wave amplitude reduction, increase for the strong force, now appears here. Right, it's a repelling force, and that is what keeps the electron from the proton. And these two competing forces will both push and pull the electron. This is proof, right? Those two forces, the attractive force and the repelling force, were solved to be the Bohr radius for hydrogen. And that now completes our table, right? 19 out of 19 fundamental physical constants now in this table solved, all with wave constants. There's a lot more than hydrogen, and so it takes an explanation of the orbital distances for all of the different atomic elements. And so one thing becomes apparent now as we use this model, which is the orbitals. First orbital, second orbital, and the number of electrons that can reside in each are based on the energy in that shell. So red slide, so pause this if you want to go through the details, but this can all be calculated based on that repelling force. It all starts with that F2 is that repelling force in number 1. Okay, but that still doesn't explain why the electron makes these jumps. It does explain finally why there's a repelling force and why it stays in an orbit, but why does it make these jumps? And there's two reasons, and both are related to the spin of the proton in the atomic nucleus. So let's go over reason number 1. First, it's important to remember the proton, just like the electron, has two possible spins. Think of it as clockwise and counterclockwise, but in particle physics, it's called half spin, positive or negative half spin. And so these symbols that you see at the bottom right are going to be used for the proton for spin up and spin down, the two different types of spin. And you'll see why in a little bit. The proton is a pentaquark structure, and so the geometry of the proton is important. So remember these two icons for spin up and spin down. So cause number one. Now imagine a wave that is going through a proton, and remember that it will pass through two different quarks, or what was referred to as probably most likely highly energetic electrons. And as it passes through, it will increase its wave amplitude. At the same time, as it passes through a standing wave structure, now that becomes, as it's a traveling wave, it then becomes the repelling force. Now, with only one proton in alignment, it's going to repel to what is the Bohr radius that was just calculated. Now, as you start to put protons in alignment, a wave might have to go through one or more protons that have their tetrahedral quarks in alignment. But when you have only two, which is helium, you have two particles of two protons of opposite spin, one spin up, one spin down. And that's the reason for using these triangles here as the legend for the proton. So you notice that there is no alignment between the vertices of the triangle. But with lithium, that's the first time that lithium is three protons. It's the first time that you can have two same spin protons in alignment. And when you do, see that wave that goes across the bottom of the triangles, now you have 2 squared. You have two protons each with two quarks in alignment now for basically 4 times the increase. And that pushes it out to the second orbital. Here is more of a mathematical description of what I just explained, because in the later sections we have to calculate each and every orbital to be able to determine a distance, and so these equations will become important. But you also notice that here is the r cubed there. That's magnetic energy. Right? It's the inverse cube. So this is a force that decreases rapidly. It's not the square of the distance rule, it's the cube of the distance rule. Well, there's 2 reasons. Right? It's hydrogen has a ground state. All elements have a ground state, but electrons can be energized and move to other orbitals. And there has to be another reason, and here's the second reason for the quantum leap. And this is based on the spin of a particle. Now the particles, the protons, just like the electrons, are spinning. And let's just call that one-time revolution. Now as a photon is absorbed, remember even a photon has a spin, it can take that energy now and the proton might spin at 2 revolutions per time unit. And so now the particle has gained energy, the repelling force is greater, and that pushes the electron out. This one is a little bit confusing to explain how resonance works, but this is a transfer, again, of wave types. But imagine a carousel. Imagine a horse on a carousel and someone pushing that horse. If you miss the horse, it does absolutely nothing for the spin, and so this is going to be illustrated here of a wave that completely goes through and misses that horse. But if you have the right frequency, the resonance frequency, then it will collide at the right time. The longitudinal wave collides at the same time that the horse and the carousel, or in this case a wave center in the proton, to be able to give it the energy to keep spinning. And so that's why the spin has to be at an integer related to the longitudinal frequency of the wave. It can't be at 1.5, or maybe it could for a brief moment, but there's nothing that continues to push it and to spin it. So it can increase to two times or 3 times, but it won't be at any other spin other than at an integer. And this is the reason for the resonance frequency. And this is the mathematical expression of it. And this is also shown, this model can be proven with what's known as the Zeeman effect. Right? So in this case, with no magnetic field applied to a particle, then it will have a certain wavelength. But when you turn on the magnetic field, these new lines start to appear in the spectral series. And one is with the spin aligned with the magnetic field, and the other is with it not aligned. So it's just the direction of the proton compared to the spin of the magnetic field. And now we're back to calculating orbital distances. Now that we understand the reason for the repelling force and the quantum jumps, the orbital distances were calculated for the first 20 elements. Only using the same concept for classical equations where the sum of the forces on that electron is 0. But it gets much, much harder to calculate once there are multiple electrons involved, because each one of those applies a force, in addition to more protons in the nucleus, and that's illustrated here. So yes, it does become more complicated, but it can still be expressed using the same concept. And these distances were validated with 2 methods. Right, calculating the distances and then comparing it to the largest orbital radius. That itself is limited, so a second method was also chosen. So calculating the distances and then comparing it to the ionization energies, which is a little bit more accurate, and that'll be explained in a second. But it had to create rules to be able to understand where the electron would be. And because of the proton's pentaquark structure, made it a little bit easier to determine where the angles might be for the electrons. And so that is shown here for the s orbitals and the p orbitals, and there's only just a couple of exceptions. And for the distance, the main distance is the distance between the electron that is being calculated and the atomic nucleus. But the distances of the other electrons also had to be estimated and solved at the same time, because each and every electron has a force on each other. And so these are the rules that were established. And here is a fun looking equation. I won't get into this in detail, but the short summary is that the electron's distance can be solved if you know the locations of each electron in the orbital and you solve everything simultaneously. Now to do this, Mathcad was used, but I'm sure almost any computer equation, computer program could be used by knowing the rules for this equation. This gets into a little bit more detail about how those forces were solved and how it became the equation. All of this is available to be downloaded on the website. You can download the Mathcad files. So let's put that to the test, right? That was an equation now that can be used to solve for the orbital distances of at least the first 20 elements. And the reason why it's the first 20 elements is the s orbitals and the p orbitals are described, but not beyond that. First one is hydrogen, which looks like this, and that was solved for earlier with the Bohr radius. But now here using the same rules that were just established, it shows it, again, just a different way. Now this is where it gets a little bit harder, right? Add a second proton now to the nucleus, and it has a stronger attractive charge. There's more destructive waves that draws the electron in closer. But there's also a second electron now that provides a force that repels it. So this third force now has to be added. And you can see that here in helium, and then the radius for helium is solved. And the reason why there is done both ways, one was manually, but now starting to show how it was solved with Mathcad, because beyond helium, Mathcad was used for all the remaining elements. So here is lithium, pause if you want. Here is boron. First time there is a p orbital. And all the way up to calcium, the pattern continues. This one is argon, and now you can see 5 different equations with 5 unknown orbitals that all have to be solved simultaneously. But there at the bottom, you see the results, and that's as a function, a ratio of the Bohr radius. All of the results were plugged in here into a table for each of the different orbitals for these elements, and other elements, ionized elements for hydrogen to calcium, were also calculated. Now, all of those results, that's how to calculate it. Now, to know if they were accurate, first they were compared to the largest known orbital for atoms. Now keep in mind, some of these are very, very difficult to measure to understand what is the largest radius distance for different elements. But here is a comparison. Pretty accurate in most cases, although you can see at calcium it's been stopped because that's the last one before we start to get into d orbitals. But there are some variations here, but again, it's important to note that the measurements of atoms are extremely difficult, so this wasn't expected to be exact. And that's why a second method was also chosen, which is to compare those same orbital distances that were calculated and compare it to ionization energies, which is more accurate. Now, to do this in the photon video, we discussed the transverse energy equation, which can calculate photon ionization energies if we know the distance. So it's cool, we now know the distance and we know how to calculate ionization energies. And this was the equation that was shown in the video on photons, and r is the distance. In the case of ionization, it's replaced with affinity. The electron leaves the atom. So therefore, since we already know the calculated orbital distance, there's really only one thing left in this equation that is variable, and that's something called the amplitude factor, which was only briefly mentioned in the video on photons. So I'm going to go into the amplitude factor in a little more detail, and yeah, this was made up. This is not common in physics, but really it makes the calculations of transverse energy a lot simpler. And so this is essentially how it works, right? 1 proton, 1 electron, that's the baseline, has an amplitude factor of 1. If you have 2 protons, it's an amplitude factor of 2. If you had 3, it'd be an amplitude factor of 3. But if you had a second electron with 2 protons, it's 1. And so that can be represented mathematically with the equation that you see there on the right. Z is protons and E is the number of electrons, and that's how you arrive at the amplitude factor. Now this works for the 1s orbital because all the electrons are in the same radius to the nucleus. And so this is a simple way to be able to do the amplitude factor for the 1s orbital. But beyond 1s, it does get to be a little bit more difficult. But the interesting thing about the amplitude factor is that it seems to follow the shapes. The 2s orbital spherical shape, p orbitals have a dumbbell shape. And so this is a table of how to calculate the amplitude factors. So now knowing the amplitude factors, and here they are, and also knowing the orbital distances, now we can actually use the transverse energy equation and calculate the photon's energy. And so here are some of the examples now. It's a red slide, so I'm not going to go through the details, but you can see that examples for boron, and you see the energy results for the photons. And now here are the results. This first one for the first ionized electron, first 10 elements, exception of helium, fairly accurate. And for the 1s electron, spectroscopy results, again, very accurate. And then this same method was applied to ionized atoms, just to get a larger sample set here. And an ionized atom will just have more protons in this case than electrons. But again, same thing, calculated the orbital distance for the electron that's being ionized and its amplitude factor, plugged it into the transverse energy equation. And this is what it looks like for the 1s1 electron for the elements through calcium. Again, quite accurate. For the 1s2 electron, and then for the electrons in the second orbital all the way to the p orbital. At the last one, you start to see some variation, and it's consistent in that variation, and there's a reason why, which is as these electrons, as there's more and more in the complexity of the atom, there's more electrons, the time difference in the force that it takes to arrive from one electron to the next one was not modeled, and so there is some variation, and it was expected. But otherwise, the results are amazing. I mean, it shows the accuracy of being able to calculate electrons and their orbital distances, and it further provides proof of that photon equation called the transverse energy wave equation, which was discussed in the last one. And that's atomic orbitals. Finally, an explanation to why the electron orbits around the proton, because it's both attracted and repelled at the same time, and this was mathematically calculated. The number of electrons per orbital is also calculated, and it's based on a conservation of energy. And the spin and alignment of protons gave us a reason for the quantum jumps of the electron. And all of this, all the calculations for elements from hydrogen to calcium, including their ionized versions, the orbital distances were calculated and compared using two different methods, validating the equations for both the orbital distance and at the same time validating the photon's transverse energy from the previous video. And that's it. A unique and very different way of looking at atomic orbitals, but finally explaining some very curious things that the electron does and unanswered questions in science. Atomic orbitals. And that concludes the video on orbitals. So in the next video, we'll take a look at electrons in those orbitals and the path that they take and the unique shapes of each atomic element. And that's up next in video number 7. Thank you.